This question gives us a graph and then asks us to find the real zeros and their multiplicities. However, note that this graph seems to have a few strange bends here on the negative side of the y-axis. When you have some strange bends in your graph, this is a clue that there could be some irreducible quadratic factors, meaning that some of our terms may end up complex. Let's check this by first looking at the real zeros. We have two real zeros on this graph. We have a -1 and a 2 as our x-intercepts, and we may notice that these cross straight through. This means that both of our x-intercepts will be first power. However, we have only two real zeros on this graph. Notice that our polynomial that we are given is x to the fourth, meaning that's fourth power. If we only see two real zeros, but we know our polynomial is fourth power, we can take that fourth power, subtract our two real zeros. When we take 4 minus 2, we'll have 2 left over, meaning we'll have two complex zeros. Anytime you have two complex zeros, this means at least one of our terms will be an irreducible quadratic. However, for part A, let's begin by finding our real zeros and the multiplicities. We know that we'll have x equals -1 as our first zero and x equals 2 as our second zero. Since they both cross, they both have a multiplicity of 1 because anytime you cross straight through the axis, that means you are multiplicity 1 or first power. As usual, let's try to get 0 on the right. So for our first piece, we'll add 1 to both sides. And for our second piece, we'll subtract 2 on both sides. If we add 1 to both sides, for our first piece, we'll end up with x plus 1 on the left equals 0, and we'll have x minus 2 on the left for our second piece equals 0. Since these are both multiplicity 1, our first term will be x plus 1 raised to the first power. We'll place the invisible 1 above it. And multiplied times x minus 2, also raised to the first power. Now we can find what our irreducible quadratic is by doing synthetic division. Let's write each of our coefficients for our polynomial. X to the fourth had a 1 in front of it, the invisible 1, of course. We have minus x to the third. Since there's no coefficient there, we'll also place the invisible 1. The same for the x squared, the same for the x. So our coefficients are 1 followed by -1, another -1, a third -1, and then -2. Inside of our first synthetic division box, we'll place that x equals -1, which was our first zero. To perform our synthetic division, we'll begin by bringing the original 1 down, and then multiply that times this number on the left. 1 times -1 gives us another -1. And then -1 plus another -1 gives -2. Then we'll take that -2 again times -1. -2 times -1 gives +2. -1 plus that 2 will give us +1. We'll also multiply that again times our -1. 1 times -1 gives -1, and then -1 minus 1 gives -2. Finally, we'll multiply that -2 times -1 to get +2. -2 plus 2 gives us 0, which means, as expected, the -1 divides evenly into our polynomial. We'll repeat this process for the other 0. We'll now divide our remaining coefficients with x equals +2. That was our other real 0. We'll begin again by bringing the 1 down. We'll take 1 times 2 to get 2. And then -2 plus 2 gives 0. We'll now take that 0 times our 2. That gives us 0. And then 1 plus 0 is 1. We'll take that 1 once again times our 2, giving us +2. And then -2 plus 2 gives 0. This means both of our real zeros divide our polynomial evenly. To find our irreducible quadratic, let's look at what's left over, that 1, 0, 1. Our final 1 will be our constant term for our irreducible quadratic. The 0 will be the coefficient in front of x, and then the 1 on the left will be our coefficient in front of x squared. This means our irreducible quadratic will be 1x squared plus 0x plus 1. And this means our polynomial can be rewritten as 1x squared plus 0 plus 1 for our irreducible quadratic, multiplied by x plus 1 times x minus 2, which were from our real zeros. This means our final answer will be y equals x squared plus 1 times x plus 1 times x minus 2. This will be our polynomial written as a product of linear factors and irreducible quadratic factors. And so by using synthetic division and our real zeros, we can deduce what the irreducible quadratic piece was.